All right, we're doing trigonometric graphs, and this is day 1, 5.3 in your books, and we're just going to be going over the characteristics and basic transformations of just sine and cosine today. So let's start with your objectives. By the end of this, you will be able to identify the graphs of sine and cosine functions. You will be able to identify the transformations of graphs of sine and cosine, and you will be able to graph sinusoidal curves and determine their amplitude. Alright, so sounds like a lot, and it is. So just bear with me and let's get into it. So let's start with the graphs of sine and cosine. So now remember from the unit circle that the functions repeat in a regular pattern. In other words, basically the only difference between like anything that's like something pi over 3 is that the coordinates, the signs change. So just it's got a regular repeating pattern, and basically every 2 pi, the pattern repeats. So if I were to add 2 pi to pi over 3, the coordinates would be identical. So, and that's because the circumference of the circle is 2 pi. Now, because any terminal point P is determined by a real number t, so in other words, t would be like our pi over whatever, and our p would be the coordinate points. And because of the wrapping functions that we talked about, if we add 2 pi to it, it has the same coordinates. So that's why you're going to see that the graph of sine and cosine are constantly repeating, and we call this periodic. So let's get into periodic functions. So we say that sine and cosine are periodic because if we have sine of t with sine having a period of 2 pi, then the sine of t plus 2 pi is also going to be the sine of t. That means so every 2 pi it repeats itself. So you're going to see that in a graph in a minute here. And the same does apply to cosine. So in other words, a function f is periodic if there is a positive number, so that's important, positive number, p, such that f of t plus p equals f of t for every t. F has a period p, then the graph of f on any interval of p is called one complete period of f. You're like, what the heck is with all these letters? Let's just imagine that t is our number, whatever it is, and p is our period. So when you look at a graph, this is like, this is one period of sine. And you can see how it's related to the unit circle. So basically, at this point on the unit circle, we go across and there's a matching point. Okay, except now we're drawing it out. So this is 2 pi, which represents the circumference of the circle. So on and so forth. So it keeps going. You got to the top of the unit circle, and that's the top here. And then it starts to go back down because the values of y start to go back down. And you can kind of see how they're related. So that's the relationship between the graph of, the trig function and the unit circle. This is the table you would use, and you'll notice that like when t is pi over 6, these are basically our coordinates. All right. Now on our graph, we're going to be using things like pi over 6, pi over 3, pi over 2, 5 pi over 6. So basically the parts of the unit circle that exist. We may not use them all. It depends on like what the size of your graph is. But everything's going to be in terms of radians for the most part. So for example, this would be the graph of cosine. Because if you notice, when we're at 0, which is right there, so that's 0, this would be 1. So 0, 1. Cosine is 1. And then we drop down to 3 over 2, 1/2, 0, negative 1/2, negative root 3 over 2, negative 1. So this would be like negative 1 down here. So this is your graph of cosine. It's going to have that kind of shape to it, that almost like a U type of shape, the parent function of it. Okay, now sine starts right at the point of origin and goes up and then dips down and comes back. So you can see how they're related, how they have the same value. So this would be like your root 2 over 2. This point right here, that'd be your negative root 2 over 2 right there. Those parts where they have the same exact coordinates in like quadrant 1 and quadrant 3, but you don't need to know those specific details. What you do need to know is the basic shape and curve of the sine and cosine graphs and kind of why they are what they are and where they are. Okay, so this would be a good thing to probably copy down or take a screenshot of and put in your notes. Okay, now, when you graph it over more than one period, it becomes a little bit more difficult to tell them apart, because now you can see that they actually look very similar. The difference is, again, without any shifts or changes or transformations, the sine crosses at the point of origin, cosine crosses at 0, 1, so 1 on the y-axis. There is ways to shift and transform these graphs so that they could overlap and still be two different functions, but we will get into that at a later date, just letting you know what is possible. So let's talk about the basic transformations of the graphs of sine and cosine. So hopefully now you know how we kind of get those graphs, and we can also transform them in ways that should be familiar to you as far as like when you've done transformations of other functions. So for example, we've got 2 plus sine of x, and then we have -1 minus cosine of x. So let's start with 2 plus the sine of x. So here's the sine of x. This 2 plus this right here. All it does, since it's a positive 2, is it's going to go ahead and it's going to just move it up 2. So that graph right there would be 2 plus sine of x. Easy as that. Alright, so now we've got -1 minus the cosine of x. So here's a cosine of x. What do you think these different parts do to it? So we have a -1. Let me fix that. So we have a -1, and then we have this here too. So the -1, hopefully you figured out, actually moves it down 1. And the negative in front of the cosine, and this applies to sine too, actually flips it. So similar to how the negative sign in front of like the x kind of flipped the graph, this does the same thing. So it basically reflects it over the midline, which we moved down 1. So if we used this to reflect it first and then moved it down, you would obtain the same graph. So it depends on how you want to approach it. Okay, so now some other transformations. We're going to be talking about stretching of sine and cosine. So again, like other functions, you can stretch sine and cosine similar to ways that you do other graphs. So, and this is nothing different. If the number or the coefficient, if you want to call it that, of sine or cosine is larger than 1, it's going to stretch the graph vertically. If it's smaller than 1, it's going to shrink the graph vertically, just like with other graphs. And remember, it has to be greater than 1, because if it's less, or it has to be greater than 0. If it's less than 0, that means it's a negative number, which means you're reflecting it before you're doing any other transformation to it. So basically we have a times the sine of x and a times the cosine of x. Now this a right here, we take the absolute value of that and we call that the amplitude, and that's the largest values that these functions can attain, and that's basically from that midline or axis, depending on if it's been shifted or not. So take a look at these three functions, and I want you, this is the basic sine curve right here. It hasn't been changed at all. This is just so you can see how these do change it. Take a minute and see if you can figure out what would happen to these. So pause it, sketch the regular sine of x, and then see if you can figure out what these would look like with it. Alright, so 2 times the sine of x, 2 in front doubles it, stretches it up and down. Okay, so instead of 1 and -1 being your minimum or your maximum, now it's 2 and -2. If we take half the sine of x, it's going to shrink it. Oh, sorry, forgot. Amplitude, 2. Okay, because of this number right here, we take the absolute value of that number. 1/2 the sine of x is going to shrink it. So instead of 1 and -1, we have 1/2 and -1/2 with an amplitude of 1/2. Okay, again, absolute value of this number. And then we have -3 times the sine of x, and we basically flip it and then stretch it. So you can see in comparison to the other graphs, it's been flipped over the x-axis, We still have an amplitude of 3 though, so we still go up to 3 and down to -3. So that hasn't changed, it's just it does it in an opposite pattern. Alright, so let's put it together and see if you can do these completely on your own. So try these two examples. We've got 2 plus half the sine of x and -1 minus 3 times the sine of x. So see if you can do those on your own. See if you come up with the same answers as me. So you should have gotten that for A, because we moved it up 2 and then half, shrunk it. And then for this one, oh, and the amplitude would have been 1/2. For this one, we moved it down 1, so notice I did that. We flipped it because of this negative sign here, and then we stretched everything by 3. It still has an amplitude of 3 though. Remember, that's from this point right here. 1, 2, 3. So that's what you should have had for those. With practice, it's going to become really, really easy, so don't worry too much about it. Alright, so now these are just some of the ways in which sinusoidal curves can be transformed. Sinusoidal curves is the like collective name for sine and cosine curves. So that when you hear me say sinusoidal, I'm referring to all of them. Now there are other transformations that we are going to discuss in the next video. They get a little bit trickier, but so get your practice in with this. Make sure you understand this, and then we'll move on tonight, tomorrow, whenever the next one is. Have a good one. Oh, and to be continued.